Good day from Las Vegas. This is JC De La Garza. I'm the NE53 technical point of contact for NEOP. My technical point of contact is Peter Swift. Filling in today will be, during the question and answer session, will be Kevin McMahon, also with India National Laboratories. The DOE Office of Nuclear Energy mission statement focuses on advancing nuclear power as a resource through research, development, and demonstration. The used fuel disposition mission focuses on the identification of alternatives and the conduct of scientific research and technology development to enable storage, transportation, and disposal of used nuclear fuel, present and future. Next chart, please. At a high level, this chart, chart 3, shows the Office of Nuclear Energy mission, R&D objectives, and enabling technologies. Note, sustainable fuel cycle is the third box under R&D objectives in the center. The DOE NE organization chart shows the Office of Used Nuclear Fuel Disposition, Research and Development. It's the center of chart, second box from the bottom, under the Deputy Assistant Secretary for Fuel Cycle Technologies. This chart shows the national lab participants that are involved in NE efforts. The grand challenge is to provide a sound technical basis for the safety and security of long-term storage, transportation, and disposal to support used nuclear fuel management and disposition pathways. Research needs under storage and transportation are the development of the technical bases for storage and transportation after extended storage, as well as for transportation of high burnup fuel. Research needs under disposal are to provide a sound technical basis for multiple variable disposal options when national policy is ready. Also, to identify and research associated uncertainty to increase confidence in concepts' robustness, to reduce the impact of site-specific complexity, and to develop the tools to manage the above. Chart 8 shows the storage system components from the pellets and the assemblies to a vertical configuration of a cask, to an independent spent fuel storage installation, or ISFSI, with a mention of monitoring systems. Chart 9 shows a visual depiction of storage, transportation, and disposal concepts and addresses the goal of technologies development and performance assessment in associated storage and disposal environments. No R&D proposals are being solicited in the storage area in the effort to pursue integrated research at this time. No R&D proposals are being solicited in the transportation area, again, in an effort to pursue integrated research at this time. University research needs for disposal include an improved understanding of degradation processes, such as corrosion and leaching for used nuclear fuel, and waste forms in materials such as glass, ceramics, or metals under variable conditions of temperature, saturation, chemical, as well as an improved understanding of the degradation processes for heat-generating waste containers, considering direct interactions with buffer materials in a repository, leading to improved long-term performance models, and then an improved understanding of the degradation processes for engineered barrier materials and radionuclide transport processes through these materials, leading to improved process models. Now, what does all of this mean? Basically, in a consent-based siting approach, we are not media specific. We can look at any geologic medium that is out there, ranging from volcanic tuffs to granites to clays. So the medium that will be looked at is open. So we're looking at all media at this time. University research needs for disposal, still continued, include an improved understanding of coupled processes in the near field of relevant disposal model environments, as well as large-scale hydrologic and radionuclide transport processes in the geosphere, leading to improved process models, as well as new techniques for in situ field characterization of properties of host media and groundwater in a borehole or a tunnel. And also, aqueous speciation and surface sorption at elevated temperatures and geochemical conditions relevant to the disposal environments under consideration. Again, the disposal environments are the geologic media that we are looking at, and we are looking at all geologic media. Finally, research needs for disposal include how specific waste forms may perform in different disposal environments using theoretical approaches, models, and/or experiments with quantitative evaluations of the long-term performance of waste forms matched to different geologic media and disposal concepts. Experimental and modeling investigations for the effect of radiolysis on disposal system components degradation under differing conditions of storage and disposal environments. Now, it's important to note that over the past 10 years, R&D has been pursued in key technical areas. Applicants that are submitting their applications are encouraged to demonstrate in their proposals a good understanding of work performed to date and to describe the need and importance of the research proposed as it relates to the safety case for a repository. This will be a strong consideration in the reviews. The previous work that has been done is available from OSTI, the Office of Scientific and Technical Information. And I'd be happy to answer any questions that we might have at this time regarding this portion of the presentation.
Please direct any of your questions to the question box in the GoToWebinar application. As a side note, something that is new this year for the FC4 area, in the past there have been 3 FC4 areas labeled FC 4.1, 4.2, 4.3. For those who have applied before, you'll notice that this in the past has been FC 4.3. On the application site, since this is the only applicable area this year, FC4 is solely focused on this disposal area that JC just outlined.
Thank you for that clarification.
JC, some questions. Is surface storage included?
No, surface storage is not included. We are looking at disposal in a geologic medium. Now, there is the requirement that retrievability be the ability to retrieve be maintained, and thus the underground storage term is used. But basically, it's underground disposal and/or storage in the event that retrievability would be required. But we are looking at underground geologic disposal.
Are you looking for fundamental studies or only studies that fold into existing repository models?
We are looking for fundamental studies. The repository models that we have are at present the strongest in a welded tough, and there is lesser strengths in other geologic media, such as clays and granite, for example. But we are interested in basic studies.
Are new materials or manufacturing methods for LWR cladding that mitigate or eliminate hydride formation and DHC within the scope of FC4 or IRP FC2?
It would be in the how the material would react in a repository reducing environment, and how it would be a part of the engineered barrier materials and would react under differing chemical, thermal, and hydro considerations, how it would react in a wet environment under different chemical conditions and different temperature conditions. From that perspective, the answer would be yes. Would this involve the manufacturer? No, not in the manufacturer, just how in the material itself would react or perform in a repository environment.
Could you provide clarification on the statement, research conducted to date? Is that research done by the university community seeking funding or DOE conducted research?
The answer is yes to both questions. It would be DOE conducted research that that is available in the license support system, the LSN, which is on the web, and also university research that has been done to date.
Are deep boreholes included in the scope?
Yes. The answer is yes.
Must engineered barriers be considered for proposed studies?
The spent nuclear fuel will be placed underground in any form as part of an engineered barrier, and the intent is to find out how the disposal components will perform from a comprehensive perspective, and we use the term engineered barrier in that there might be, just for talking purposes, there might be, say, a bentonite placed around the package itself, and we would want to know in a elevated temperature environment and under different conditions of moisture and chemical processes, how the entire engineered barrier, or how all the interactive components would perform over an extended period of time.
Can the safety analysis guide for Yucca Mountain be used for this proposal?
If I understand the question, the safety analysis guide would be a useful source document for the development of a proposal.
Are you interested in measuring the heat, reactivity, initial enrichment, burn-up, and cooling time of individual assemblies?
All of those parameters would be a part of the picture, if you will. They will be data points that would involve the performance of both the waste package and the surrounding engineered barrier. So all of those would be key inputs to the total system performance. The short answer is yes from that perspective. How they affect the total system performance, being the waste itself plus the engineered barrier in the underground environment.
Is there a specific location for previous university research, or are you referring only to previous FC4 funded projects?
We are referring to university research under NEAP funded projects, as well as prior research that has been done that is available on the License Support Network, the LSN, which is available on the web.
Would the development of dry cask storage systems be considered part of this scope?
Dry cask storage systems are, no, that's outside of the scope. That's a surface storage consideration, and that's outside of the scope. We're looking at underground, geologic emplacement. Okay, this is cask misloads evaluation techniques, IRP. We're looking for a 4-year effort, $3 million total project cost. Again, I am the NEAP FPOC federal point of contact. Peter Swift will be the technical point of contact. Kevin McMahon will be filling in for Peter Swift. There are many types and designs of spent nuclear fuel casks and containers currently in storage around the country at various nuclear power plant sites. The inventory of spent fuel in these casks containers is large and with varying burn-up rates and out-of-reactor times. The casks and containers have multiple internal components that are designed to provide structural integrity during storage and in some cases during transportation. The long-term stability of the internals and spent fuel and its cladding is important to maintain subcriticality of the fissile materials in the casks containers. The challenge is to assess the condition of the internals and the spent nuclear fuel non-intrusively during the normal conditions of transport and hypothetical accident conditions. This research topic addresses the development of innovative technologies to determine the extent of any damage or degradation of internal components during transport that includes normal conditions of transport and possibly hypothetical accident conditions. There are non-destructive examination techniques currently in use where surface damage and in some cases volumetric assessments can be performed on a reasonable scale on metal components. The technology becomes limited when layered and inaccessible components with different materials and varying gaps between the layers are encountered. Needed are fundamental technologies to discern the condition of the internals of a spent fuel storage cask, that is, the baskets and the assemblies, during normal conditions of transport and hypothetical accident conditions that are specified in the NRC Transportation Regulations 10 CFR 71 with a high degree of reliability. Prior work focused on static applications after prolonged storage, while this work focuses on dynamic applications during transport. Now what that means is there was a previous IRP that was presented last year, and that IRP looked at attempting to get an idea of the condition of internal components after prolonged storage, but prior to transport. And we would be looking at components that were in storage and that could be viewed with a greater degree of ability, if you will, to look at them in a static state, in situ. The intent now is to be able to look at internal components in a more dynamic situation where they are being transported and or have been subjected to hypothetical accident conditions. The development of new technology or technologies to support the design of simplified tools that can be used for assessing, cataloging, sorting, and isolating any operationally degraded casks or canisters during transport is the objective. Work to be performed. Innovative methodology development. Describe the underlying fundamental principles along with a description of the technology to be developed with an assessment of any limitations. Justification for how the technology will be successful should be provided based on any experimental or analytical studies that may be available. Proof of principle evaluation. Develop and demonstrate feasibility of the methodology for multi-layered and different material systems. Here, the opportunity exists to establish the degree of conformance to the initial expectation of performance and provide any refocus needs. Identify and quantify inherent uncertainties. Systematically develop uncertainties associated with a methodology and its application to a basic system. All non-destructive evaluation systems have both bias and uncertainty. It's important to understand and quantify these biases and uncertainties to incorporate the uncertainties in the data evaluation process. Develop and implement a mock-up test program. To the degree possible, tests should be conducted initially on a cask or container with no fuel elements, and then follow up with a structurally representative fuel internals. At this stage, no irradiated materials need to be considered. The test results should provide calibration for the use of the developed technology system to similar enclosed cask container designs. And then prepare a detailed final report. The report will document the R&D elements of the IRP, provide bias and uncertainty in the system, and discuss the lessons learned from the effort. Task to be performed. Task 1, development of an integrated plan, technology development and testing 3 to 5 months after the beginning of the performance period. Task 2, methodology development. This is due 9 months after the beginning of the performance period. Task 3, proof of principle testing and uncertainty evaluation. 15 to 18 months after beginning of performance period is when that's due. Task 4, develop and implement mock-up tests. This is due 26 to 32 months after the beginning of the performance period. Task 5, analysis of test results and benchmarking of model at 33 to 40 months after beginning of performance period. And then Task 6, complete project report 48 months after the beginning of the performance period. We have extended this to 4 years to allow more time for development. The deliverables consist of a technology assessment report 24 months after the beginning of the performance period, and then the final project report due 48 months after the beginning of the performance period. A final project report will be delivered that documents the work performed and discusses the final conclusions and recommendations, as well as the technologies developed and how they can be effectively implemented. And that's my last chart. I'd be happy to answer any questions that we might have at this time.
I forgot to mention after the FC4 topic, but we do have Kevin McMahon on the phone who is available to answer questions as well. First question. This is regarding the FC4, not the IRP. Most proposed studies consider the full system performance, or can a subsystem be studied, i.e. radionuclide transport post-barrier?
The answer is yes. That would be a focus area within the total system, but we would consider it. The answer is yes.
For the IRP, would an active IRP be limiting for an applicant? And I can answer this question. This is more of a procedural question. An active IRP where the PI is the lead PI is restrictive to be able to apply to a new IRP. You are a collaborating PI or a co-PI on an IRP, then having an active IRP is not restrictive to applying for additional R&D funding or an IRP. Next question, is the object of the study the cask or the canister or both?
The object of the study is to get a peek at the internals. Primarily, we're wanting to find out the condition of the assemblies and the rack that, if you will, that holds the assemblies, to find out if in effect they have been jarred or loosened or bowed, or just to what degree that they have sustained any damage, damage if any. And then we would have the intent of cataloging and or isolating, if necessary, a canister with damaged internals. But the focus is to get a peek through innovative technologies to get a peek at the internals.
Last year it was asked to contact utilities for on-site testing of dry casks. Is this still required in this year's IRP?
That would be useful. It would be useful, and it would be considered in the application.
This is a similar question. Is a collaboration with the cask company a requirement?
Could you ask the question again, please?
Is collaboration with a cask company a requirement?
It would be a part of the proposal. It would be a plus in the consideration. That would be part of the evaluation of the proposals.
But it's not required then, JC?
It is not a requirement.
Okay. You mentioned that these techniques need to be non-invasive. How close to the fuel can we get?
The canister walls are as close as we're going to be able to get, because we do not want to breach the canisters, and that would be as close as you can get. Now these canisters will be in transportation overpacks, and therein lie the reason for indicating that you would want to get, if there's a way to get under the overpack to the wall of the canister, that would be a plus. But we want an innovative method or technique to be able to get as close as we can to the walls of the canister and be able to take a peek, if you will, inside without breaching the canister.
Will the mock-up have to be a 1-to-1 in real size, or can it be scaled down for lab testing?
The size of the mock-up is a part of the proposal that is subject to the capabilities of the offeror, and that would be a part of the consideration. Of course, the larger the mock-up, the more accurate or relevant the results. But that would be up to the discretion of the offeror.
Is determining fuel burnup a requirement?
There will be differing levels of fuel burnup involved in the canisters. That information should be a part of the existing information on individual canisters. But if there's a methodology that would be developed that could determine or verify that degree of burnup, that would be considered a plus. Kevin, do you want to add to that?
No, I think you covered it just fine, JC. I think that's exactly right.